Hi everyone and welcome back to my YouTube channel. Today we are going to continue exploring the problem of the fox in a hole, but this time we're going to take a more optimization approach. So what we're going to do is to build a mathematical formulation that is going to enable us to solve the fox in a hole problem. And to do so, we will have to first define the parameter and the variable and see what we want to minimize or maximize, because this is what we do with optimization problem. You want an objective function that you want to optimize at the end. So the way we are going to start this problem is to define the sets. So what are the sets that we are considering for the fox in the hole problem? So the first thing we are going to consider is the holes. So we are going to note the holes H. And so for the problem we had before, we were having the holes number 1, 2, 3, 4, and 5. But really we can generalize the problem and use as many number of holes as we want. The other set that we have to consider is the days, because we can catch the fox in day 1, day 2, day 3, etc. So we are going to note the days D, and we are going to say, yeah, like that we can have as many as we want. Let's say for now that we can go up to the number 10. Because we know that for the 5 holes problem, we should be able to catch the fox in 6 days. So let's take a number of days that is a bit larger than 6 and arbitrarily take 10. Another set that we have to take into account for this problem is a scenario. What I mean by scenario is that to solve this optimization problem of the fox in the hole, we have to consider that what's happening is that we want to catch a fox and we don't know which path the fox is taking. And we are going to consider that we want to catch the fox regardless of the path the fox has been taking. And the path can be seen as a scenario. So what we are going to take into account is all the possible path of the fox or the possible scenario, and make sure that we will catch the fox regardless of the scenario we are in. So let's write this additional set. So scenario S, that can go from 1, 2, and we don't know exactly yet how many scenarios we will have. Intuitively, we know that it will depend on the number of days. For example, if we have only 1 day, the number of scenarios is exactly 5. Why? The reason why is because the fox can only be in 5 different holes the first day. So in the first day, it can be in hole number 1, 2, 3, 4, 5. So we have exactly 5 scenarios, no more than that. For 2 days, it will be a bit more complicated. But we are not going to calculate that in advance. We are going to let a Python algorithm solve that for us, and we are going to spend time on that later. Let's just assume for now that we have a certain number of scenario S that we don't know in advance, but that are representing, that is an exhaustive list of all the possible paths that the fox can take. Okay, so now we are going to describe the parameter of the problem. So for the parameter that we are going to take into account is a parameter that depends on HD and S, the hole, the day, and the scenario, and we are going to call fox DHS, and this parameter is going to be equal to 1 if and only if the fox is in hole H, in day D, in scenario S. So let's assume that we have this parameter that is telling us for any given scenario, day, and hole, like if the fox is here or not. And if the fox is not in this hole, day, and scenario, it's going to be 0. So we are going to have 0 otherwise. Okay, perfect. So now what are the variables of the problem? So we are going to first define a variable that is check. So we are going to check regardless of the scenario we are in, and we are not sure yet if we are going to catch the fox or not. So let's call this variable check dh, and it will be equal to 1 if we check whole h in day 1. Okay. So now a variable that will depend on the scenario S is catch. And this will depend on the day, the whole, and the S. And catch will be equal to 1 if and only if we catch the fox in day D, whole H, and scenario S. And it will be equal to 0 otherwise. Intuitively, we know that we can only catch the fox if the fox is in this whole day and scenario, and also if we check this whole in that specific day as well. So basically, we know intuitively that catch DHS is equal to 1 if check DH is equal to 1 and if fox DHS is equal to 1. But there will be other conditions that we are going to see while we are continue to build this problem. So let's continue defining the problem here. So we are going to have another variable that this time is not going to depend on the whole itself. We want to know if in a specific day and scenario we catch the fox regardless of the whole he is in. So we are going to call this variable catch in whole, and it will only depend on D and S. And again, it will be equal to 0 or 1. And it will be equal to 0 if we don't catch the fox in that day and scenario, and equal to 1 if we do catch it. Let's define another variable that will be called cut. What this variable is going to do, it's going to basically tell us if we have previously caught the fox in the previous day. So it will be equal to 1 if we caught the fox in D that is, I should say, in a day that belongs to 1, 2, etc., D minus 1. And it will be equal to N scenario S. And this is going to help us like not do too many check, because we also want, for the stability, let's say, of the problem, to stop checking once we have already caught the fox. But again, I'm going to spend more time explaining how we do this. So another variable that we can define is caught all scenario, that this time is only going to depend on the day. And this is going to be equal to 1 if we caught the fox in the etc. In all scenario. Caught all scenario is going to be related to the variable caught. We will only have a caught all scenario if all the variable caught in that specific day in all the scenario will be equal to 1. Another variable that we are going to define is catch day, that only depend on the scenario S. And this is going to give the day in which the fox is caught for a specific scenario. Right there, specific S. Okay. And finally, the last variable that we are going to take into account, And this is where finally the problem is starting making a bit more sense and connected to the problem that we have seen in the previous video, is the catch day max. So what is the catch day max? The catch day max is basically the latest day in which the fox has been caught in all scenario. So what's going to happen, and we can see that already, is that this catch day max is going to be greater than all catch day and is going to be equal to the maximum among all the scenario of the variable catch day. So this is what we are trying to do at the end. We want to have an optimization problem that is going to minimize the catch day max, because we want to find a strategy, a checking strategy basically, where we are going to make sure that the catch D represented here is going to be not greater than a specific variable catch day max, and we are going to minimize this maximum number of days before we catch the fox. Okay. So now let's define the equation of the problem. So maybe before we should directly say what we are trying to minimize. So again, for this optimization problem, we want to minimize the variable catch day max. Okay. So now what are the equation, the constraints that are going to give some rules inside this problem? So one of the first rules that we can take into account is that if the fox is not in DHS, then we are not going to catch it for sure. You cannot catch a fox that is not in a specific place in time and in space and in a specific scenario. So the first rule that we are going to put in this optimization problem is that if fox DHS is equal to 0, then catch DHS is equal to 0. And so in an optimization problem, what we are going to do is that we are going to make sure that this variable will be fixed equal to 0. Something that we should say before we start actually diving into the optimization problem is which kind of variable we are defining here. So as I said, we have the parameter fox, that is just a parameter, so we don't have to worry about this one. But for the variable, so check is a variable that is going to take the value 0 or 1. So we are going to see like which kind of variable we must use for each of the variables we have previously defined. And we are going to see that in theory, most of them should be defined as binary, but we are going to see, thanks to some trick, that actually not all of them must be formally defined as binary. Some of them can be perfectly defined as linear, and we are going to see that they will be implicitly binary. But the fact to replace binary variable by a continuous variable is helping a lot to solve the problem, because in an optimization problem and in a mixed integer linear programming problem, the less binary variable we have, the better it is for the problem. So check DH, as we were saying, is going to be a variable that should take the value 0 or 1. So a priori, it is a binary variable. Catch also is a variable that should take the value 0 or 1. So it's also supposed to be binary. Catch in whole is a variable that is going to take the value 0 or 1. Do we catch the fox in that specific day in that specific scenario? So let's put the symbol B for binary. Caught DS, same thing. It's equal to 1 if we have previously caught the fox, otherwise it's 0. Caught all scenarios 0 or 1, so binary. So as you can see, not a lot of continuous variable, but we're going to see that actually most of them can be defined as continuous. Catch day is not binary because it's going to give the day number in which we catch the fox. So it's going to be equal to 1, 2, 3, 4, 5, etc. So this is actually, in theory, defined as an integer. And catch day max is also defined as an integer. Okay, let's go back to the equation. Another thing that we can say is that if the fox is actually in the specific hole in that specific day and specific scenario, so if fox DHS equal 1, then in that case we have a chance to catch the fox, but only if we are checking that hole. If we are not checking it, then we are not going to catch the fox for sure. So in that case, what we can say is that catch DHS is lower than check DH. And again, the reason why is because if check DH is equal to 0, we don't check the hole in that specific day, then in all possible scenarios, we are not going to catch the fox. Okay, let's continue with that. We have found the upper bound for catch. Can we find a lower bound for catch? And we are going actually to define one. So we consider that we are still in that hypothesis that the fox is in that specific day, hole, and scenario. What we are going to allow is that we do not necessarily catch the fox if we check, but if the fox has been caught before in that specific scenario. So we are going to write things this way. So catch DHS is greater than check DH minus caught DS. And so the reason why we can write that is that even if we do check in a specific day on a specific hole, if in one specific scenario S the fox has been already caught, we are not considering that we can catch it again. Because at the end of the day, we want to be only able to catch the fox one time per scenario. Okay. So now let's continue. The rule of the fox in the hole game is that you cannot check more than one hole per day. So this can be translated into an equation, and this equation is that the sum among all the hole of check DH should be lower than 1. But actually, we can find a better one. What's going to happen in practice is that we should keep checking until we are sure that the fox has been caught in all scenarios. So this equation, we can actually delete it and replace it by a much more interesting equation, which is that the sum over all the whole of check DH is equal to 1 minus caught all scenario for that specific day. So what does that say exactly? This equation is saying that if we do not guarantee that we have been able to caught the fox in all possible scenario for that specific day, then we are going, this value will be equal to 0, and we are going to check in at least in exactly one hole. But if we say that we have found the fox, we have caught the fox in all possible scenario at that day and for all the days after, then this variable will be equal to 1, and at the end this will be equal to 0, and we are basically saying please do not check because we know that the fox has already been caught. Okay, and we can see that this equation right here gives actually more information and is better than the one we were previously writing. And one thing that we can notice is that this equation ensures that check DH equal 1 for at most 1H and not more than that. And this is actually something interesting because we have seen in the previous equation right here that catch DHS is always lower than check DH. So this is also going to say that catch DHS is equal to 1 for at most 1H. So this is implied by this specific equation that we have seen above. Let's continue with more constraints. So now we are going to go to constraints that are easier to understand. One equation is the catch in all. So the variable catch in hole is going to be equal to 1 if we catch the fox in one day, whatever the hole is. So catch in hole ds. And so because it's going to be equal to the sum of catch dhs, the sum over all the whole. And the reason why we can write that, and we are sure that it's going to be a maximum equal to 1, is because we know that khdhs will be equal to 1 for at most 1h. So this will always be lower than 1, and it will be equal to 0 if we do not catch the fox in that specific day and scenario. Okay, let's continue. So now we are going to define the variable coat, which is a bit trickier to explain. So the variable coat is going to be basically equal to 0 at the beginning and then equal to 1 for all the day after once we catch the fox in a specific day. So this variable is going to be equal to coat of the previous day plus catch in hole ds. And so what's going to happen is that at first this variable will be equal to 0, and as long as catch in hole is still equal to 0, coat is going to stay equal to 0. But as soon as we catch in hole in a specific day, then in a day right after, we will have this variable that will be equal to 1, and then the consecutive variable for all the consecutive day that will be equal to 1 as well. So this variable will basically equal to 0 for a long time and then equal to 1. Okay, so we should maybe specify an initial condition for that variable, and that makes sense to say that coat in day equal 1 in scenario S, it will be equal to 0 for all possible scenarios. And the reason why we say that is because even if we catch the fox in the very first day, it has not been caught before the day 1. So we can perfectly define that this variable is equal to 0 in the day 1. Okay, let's continue. So now we are going to define the variable caught all scenario that only depend on D and not the scenario because it's for all the scenario. And basically this will be equal to 1 if and only if caught ds is equal to 1 for all scenario. So this is okay to write it mathematically this way, but we have to find some linear equations so we can integrate it into the mathematical programming problem. So we cannot write this in the optimization problem, but what we know is that this cannot be equal to 1 if at least one of the caught ds is not equal to 1. So what we can write first as an equation is that caught all scenario d is lower than caught ds for any s. So if one of the s will be equal to 0, this will also be equal to 0. But if all of the caught ds are equal to 1, then we want this to be equal to 1 as well. And the way to ensure that is to use a lower bound where we say that caught all scenario d is greater than sum for all the scenario of caught ds minus number of scenario plus 1. So why do we write that? Because if all the caught ds are equal to 1 for all the scenario, then we will have a sum for all the scenario of 1. So we will have this sum that will be equal to ns minus ns is equal to 0 plus 1, we will guarantee that this variable will be greater than 1. And if one of them is lower than 1, then this sum will be at most equal to ns minus 1. And so we guarantee that this variable will be just greater than 0, but not greater than 1. So this is perfect. These two equations guarantee this necessary and sufficient mathematical condition that we wrote just above. Now let's go to the two last equations. So one equation is about the catch day for a given scenario. So this catch day of a given scenario is going to give the day index in which we catch the fox. So the way we can define this equation is as a sum over all the d of d multiplied by catch in whole ds. So why does it work? Because we know that we are going to catch the fox in a hole for a specific day, and if it's for the day number 7, let's say, and not the other day, then we just multiply this variable that will have the value 1 by the day number that will have the value 7, and this will be equal to the day number in which we catch the fox. And so this works perfectly. That gives the day in which we are catching the fox for a specific scenario. Another equation that we should write is that we want to, for any given scenario, we want to catch the fox at least once. So one way to ensure that is to make sure that this catch day variable is greater than 1. This ensures that at least one of the catch in the hole variable in a given day will be equal to 1. And so we make sure that we catch the fox in at least one day in each given scenario. And finally, the last equation that we can write is the fact that catch day max must be greater than catch day for all possible scenarios. And because this is the value that we are trying to minimize, we are going to try to minimize all the catch ds at the same time, and this value will be equal to the max catch ds among all possible scenarios. So these two equations together ensure that the optimal value of catch dmax is the maximum number of days necessary to catch the fox in all scenarios. So now what we're going to see is to check if the way we define all these variables necessarily has to be binary, or if some of them can be defined as linear because it will be implicitly binary because of the equation. So let's assume that the variable checkDH is defined as binary. And let's see what would be the consequences for the other variable. So one variable that we see here in that equation, quote all scenario D, is defined with a equality. And because in that equation, this sum is guaranteed to be between 0 and 1. And so that implies that this has to be between 0 and 1. And so the variable quote all scenario is guaranteed to be between 0 and 1. But even better than that, because checkDH has necessarily an integer value, and this is also an integer value, then this implies that this necessarily has to be an integer as well, that is between 0 and 1. So this variable will be implicitly a binary variable, even if we define it as linear. So we can take away the condition that quote all scenario D has to be binary. Even if we define it as linear, it will be implicitly binary. So another thing that we can see is that if the variable quote ds was defined as binary, because of that equation, catch in all necessarily has to be binary as well. It cannot take any other value than integer value, and specifically binary. So forcing code to be a binary variable ensure that catch in all will also be a binary variable. Additionally, forcing catch in all to be a binary variable, so only equal to 0 or 1, will also guarantee that this value, the catch, will also be equal, will also be binary. And the reason is each catch is lower than check, and we cannot have more than one check equal to 1 per hole. Then this implies that we have most of the catch are equal to 0 for most of the h, and we have at most one catch that is strictly greater than 0 but lower than 1. And if this is equal to 1, then this only catch value will also be equal to 1. On the other hand, if catch in all is equal to 0, this means that all the catch must be equal to 0. And so this proves that catch can only take the value 0 or 1. So what we just said before is that if code is binary, this implies that catch in all is binary. And this implies as well that catch is binary. And what we mean by binary is that they can only take value between that are either 0 or 1. So now what we are going to prove is that code, without having to explicitly define it as binary, will still be binary. So let's assume that for a given S, for a given scenario, we have cut ds that is equal to 0 for a specific day. Then in that case, we saw from the inequality above that catch DHS is between the bound check DH and check DH minus cut DS. So as long as we have cut DS is equal to 0, we can take off this thing and we have catch DHS that is exactly equal to check DH that is defined as a binary variable. So this variable will also be implicitly binary, even if we define it as linear. And what's going to happen is that the first day that cut ds will be greater, strictly greater than 0, then we will have cut, thanks to the equation that we have seen above, we have cut ds that is equal to cut d minus 1 s that is equal to 0 because it's the previous day, plus catch in all that is nothing different than sum over h of catch dhs that t minus 1, because it is equal to 0 in the previous day, it is implicitly binary, and this implies that catch in those previous days is also implicitly binary. And so because we have code that is equal in d minus 1s that is equal to 0, and all the catch d minus 1 hs that is implicitly binary, then this is also implicitly binary. And because it is implicitly binary and it is strictly greater than 0, this implies that for the first day that cut ds is strictly greater than 0, we will actually have cut ds is equal to 1. And we have seen that because of this equation above, once we have a cot ds that is equal to 1, in all the consecutive days, the cot ds will be also equal to 1. So we will have cot ds, which will be equal d prime s, which will be equal to 1 for all d prime that are greater or equal to d. So at the end, what we have is that cot ds is implicitly binary, so we don't have to define it as binary. Catch in all is also implicitly binary. Catch is also implicitly binary. Catch day will be equal to a sum of a product of integers, so it will be implicitly an integer. And finally, catch dmax is something that is greater than all this integer and will be also implicitly an integer because it will be by minimizing it, it will be equal to the max of all of them. So finally, the only variable that we really have to define as binary is only the variable check. So now what I'm going to show here is the code that is going to allow us to solve this optimization problem. So the first important part of the code is that we define the number of days and the number of holes. And we are going to define all the possible paths that the fox can take. So the way we are doing this is that it will depend on the number of days. And what happens is that if you have only one day, the number of scenario will be exactly equal to the number of the holes, which is 5. Now, what happens if you have 2 days is that for the first day, there are at first 5 different scenarios, but then for the day 2, the hole can jump either to the left or to the right. So you multiply, in theory, the number of scenarios by 2. But of course, some scenario will not be feasible. For example, if we consider the hole number 1, so the hole that is all the way to the left, and the path in which the fox jumped to the left, then this path is not feasible because the fox is jumping to a place where there is no hole. So what we are doing in this code over here is that we are first calculating all these possible paths by multiplying by 2 each day the number of scenarios, even if some of the paths are not feasible. And after that, we are going to check the feasible path by checking if we are jumping at a hole that is between 1 and 5, and if we are jumping in a hole that is lower than 1, strictly lower than 1, or strictly greater than 5, then we are going to eliminate this path. So let's run this code. And so what happens is that when we have 10 days and 5 holes, we can see that the number of scenarios will be equal to 648. This is guaranteed to represent all the possible paths of the fox. So now we are writing the optimization problem here by describing the set days, hole, and scenario. And all the previous equations that I was describing before are written in code by all these different lines. So we are going to run this code and see what will be the solution of the problem. And hopefully we will have a solution that is similar to the one that we got in the previous video. So if you didn't watch the previous video, I will remind that the optimal solution that we were having just by looking at the space-time diagram of the path of the fox was the solution 432-432 or 234-234. So let's run this code and wait until we obtain a solution to the problem. So as you can see, we finally got an answer to our problem. The objective function value, which is the maximum number of days that we need to catch the fox in all scenarios. As you can see, the optimization algorithm is not perfect, so we can see that the answer is supposed to be 6, but instead we have a 5.99999, many 9 after, but this is basically, the solution is basically the answer 6. And I have saved the optimal solution of the variable check that we have explored before. And so if we open the variable check that is right here, this is going to give for each hole and for each day the strategy that we need to use to catch the fox. And as you can see, we observe something that is slightly different that we have said before. We were saying that the best strategy was to do either 2-3-4, 2-3-4 or 4-3-2, 4-3-2. But actually, nothing prevents us to do 4-3-2 first and then 2-3-4, or it could have been the other way around. So we see that the optimal solution is equal to 6, the number of days in that case. But what we are going to try to do is to fix some of this check value to see if we are going to change the optimal solution. But a priori, we should still have an objective function value of 6 if we start with that day and if we start with that day. So let's try this. So we are going to uncomment this part of the code here and say that we are going to check, so for the day number 0, so that's the day number 1, and the whole number 1, we are going to set the initial value of 1, and we are going to do the same thing, but for the day number 0, 1, 2, so the day number 3. And we set the initial value at first, and then we are going to fix the value and see what we obtain. So let's run the code again right here. So as you can see, the objective function value is still equal to 6, and we are going to open the check var. And here we are seeing the same path as we were seeing before, and we can still see that that solution is also optimal. What we can try to do is to mess up a bit with the solution by giving a strategy that we know is suboptimal. So let's say that we want to first to check the first hole in the day number 1, and the rest is the same. So maybe let's comment this part, and let's comment this part again. So here what we are forcing is that we check the hole number 1 in the day number 1. And normally we have seen that this solution, we have seen that in the previous video, this solution should be suboptimal. So let's try it and let's run the code. We got the solution, and as you can see, we are not obtaining 6 that we know right now is the optimal solution of the problem if we are not fixing any value. If we force the problem to check the hole number 1 during the day number 1, then we are having a suboptimal solution, and let's see the strategy that we are having in that case. So what is interesting is that we are still having a diagonal path that is basically very similar to the one we were having for the optimal solution, but except that the only difference is that we start applying the optimal solution from the day number 2, and in the day number 1 we are just forced to check the first hole. So that's it for me. I hope that you like this video and that you like this optimization approach to the fox in a hole problem.